Okay, welcome everybody to the clinic. My name is Gil Fuchs, and just to give you a little bit of background, I was infected with this model railroading bug by my father since I can remember myself. We always had a model train, a small layout, a table, something going on. And since I'm also by profession, I'm a double E. I actually combined both things, both of my hobbies, and contributed a little bit to the electronic side of model railroading. Some of the things I worked on, I was a member of the NMRA DCC working group, working on parts of the NMRA DCC standard. Both connectors, testing, some of the specifications and so on. And also, and this is going to be a shameless plug, we have a control bus for layouts, which is called C-Bus. And especially for those guys who are interested in building your own, doing your own DIY in electronics for model railroads, this is Haven basically. Go to the MERG website. They have kits, a series of kits. You can construct an entire system at a fraction of the cost of what's going to cost you commercially, and enjoy it. And I think it's a lot of fun. So given this, we have a couple more housekeeping items to cover. First of all, I use the term keep alive throughout this presentation, and keep alive is actually a registered trademark of TCS, Train Control Systems. I talked to Train Control Systems and I asked them if that's okay with them to refer to these devices as keep alive. They said yes, of course. Just remind everyone that it's our registered trademark. So we've done that and we covered that part. And secondly, this clinic, as was mentioned, of an earlier version was given in one of the Potomac Division mini-cons, I believe in 2018 or 19, I forget the exact date. This one is sort of an update with a few more development that happened in the industry, and we'll give you a little bit more current information. I'm not going to give you a full, this is not a workshop for constructing your DIY Keep Alive device, but I think it'll give you enough in order to get started, to get some ideas and how you can go about it. And so basically, Keep Alive devices, those are energy storage devices that we use to keep our engines running even when they hit a dead spot on the track. There's no power supplied, and we need to go over the gap or clear that bad spot, or overcome that problem. So this is what Keep Alive is used for. And the other thing is that, as a side effect, it also acts as a filter and smooths out, the DCC signal that you're getting from the track and the power. So subsystems like sound, and other systems that you may be using are going to work better if you add a Keep Alive device. Can anybody see the next slide? Miss MR Life is not perfect. Yes. Okay, so as we know, locomotives tend to stall on switch points. Personally, I use my track is Marklin, which is a 3-rail system, and one of the problems with it is that it's got sort of small dead spots, especially in turnouts, and the engines tend to stall there. And that was a good enough reason for me to install Keep Alive devices in as many engines as I could, to basically prevent that stalling. It's quite annoying when you're switching, when you're running an op session and people are switching, and all of a sudden they get, your switcher hangs on one of those switches and one of the points, and it disrupts the operation, and people didn't like it. So Keep Alive's definitely help, in that respect. Also, despite, I'm sure that all of us clean our track day and night, but we always still have some dead point, dirty track spots and bad connectivity and corrosion that happened and wasn't cleaned and so on, and some gaps in the track because, life isn't perfect and your wall wasn't exactly square. And anyway, DCC in particular, if you switch to DCC, requires even better quality and better connectivity than what we used to require with AC and DC systems. So all the more, we need that extra power injected to our engines to be able to run them smoothly. And I mentioned sound. So if you do have a sound system added to your decoder, a sound decoder, Keep Alive is sort of a big container of energy, right? And sound engines require a lot of juice. And when you add this Keep Alive and it's fully charged, even if you have limits on the current that you can consume from the tracks, your sound system still gets whatever it needs, from the reservoir from the Keep Alive, and it keeps charging. Okay, should you use a Keep Alive? There's some pros and cons here. I mentioned smooth running of locomotives. The locomotive keeps going. Now that's a double-edged sword because yes, your locomotive is going to go across the gap and it's going to, now we have Keep Alive systems that run for about almost up to about 30 seconds and sometimes more. And so your engine's going to keep running. But if you don't take care of it, and we'll talk about what you need to do, they'll keep running even when you don't intend them to. And that means that, you cut the power to the rails, you have an emergency, some engine acting crazy, you cut the power to the rails and your engine keeps running. And, in the good case, it'll just stop somewhere. In the bad case, it'll fly off your track. And, I don't want to talk about that kind of disaster. There's less disruption to sound. We talked about that, filtering. And there's one additional advantage for using Keep Alives is that it extends motor life. And most of our motors are what's called brush motors. They have brushes that, deliver the current from the track, from the decoder to the rotor part of the rotating part of your motor. And if you have a Keep Alive and your current is smoother, what happens is that you have less sparking and less arcing of those brushes when they contact the rotor, the commutator, what's called. And as a result, your motors tend to live longer. On the con side, sometimes Keep Alive would actually worsen a short situation and conduct more current, and pump in more current and more power, and make arcing actually more severe. So in general, it is an advantage. Sometimes it works against against the healthy running of the engine. So a little bit of the cons. The biggest disadvantage of using a Keep Alive is that it requires an additional device installed in the locomotive, and that device typically is not a small one and definitely not a thin one. So now you have your decoder. You have to, I'm guessing that if it's a sound decoder, you reserve some space for a speaker. And if you want any quality of sound, it has to be a little bit more than the smallest speaker available. And now you have to add this device, which has capacitors, and it takes up space. So if you are running large diesels, you probably have less of a problem. I mean, you might have to cut some of the frame there to create space if it's filled with iron or something. Otherwise, there's typically enough space in diesel locomotives, large diesel locomotives, to install the Keep Alive. With steam locomotives, small switchers, and especially European engines, if you're running any of those, it's going to be more of a problem. And we'll talk about some of the solutions. Mostly keep alives are installed in, are used in HO scale now, but there are already some offerings for smaller scales like N scale. We'll talk about that too. But obviously, in N scale, installing a keep alive is a lot more problematic. You're going to have a lot more space restrictions and so on, while your voltage requirements and power requirements are not that different. They're obviously lower than HO, but not that much lower. So we'll talk about what can be done. Decoder compatibility. So, some of the decoders, in general, keep alive devices can be connected to most decoders. There are very few old decoders that do not react well to keep alive devices. And what they would do is they would either switch to DC mode in the presence of a keep alive and stay there and, stop responding to DCC commands, or they will refuse to program, or, they'll just stop responding altogether. So I've seen all cases, but very few decoders that act that way if they're set up correctly. And you need to program the decoder correctly in order to prevent some of the most common problems with it. And we'll talk about that. Some of the older decoders, I had a few MRC decoders that were, very, very basic. They did not react well to the addition of a keep alive device. Other than that, almost all other decoders worked fine with the keep alive device. Some decoders add extra control, to the keep alive arrangement, and that makes the keep alive device more efficient. So basically, you'd see two wires typically connected from the keep alive to the decoder, plus and minus. If there is a third wire that's getting used, that's getting connected to the decoder, that's typically a control wire. And what that does is it will command the keep alive. The decoder actually sends commands to the keep alive to shut down or start, pumping current, and, saving a lot of energy that way. So that typically means that you're going to have to purchase the keep alive and the decoder from the same manufacturer if you want to get that extra efficiency. If you don't care about that, you can basically mix and merge. There's not a lot of limitations. And those devices are now marketed by most DCC vendors. So we'll talk about a couple of the families of keep alive devices later, but in general, most of the vendors have them now. A few of the other problems that you may be encountering: difficulties in DCC programming. We'll talk about the reasons for that, but the main thing is that, DCC, the way that programming is done on the programming track, on the service track, is that you're getting a current signal back from the decoder. So the decoder basically opens up a device like the motor or the lights or something like that and draws current. And when it draws that current, the programmer senses it and knows that the decoder actually responds, received the command, received the programming command. And we call this an ACK, or an acknowledgement. And what happens is when you add a keep alive device, sometimes that ACK or that current gets swallowed in the current that the keep alive device consumes, charging itself. And when that happens, obviously the programmer gets confused. It doesn't know when exactly the packet was, acknowledged, whether it was acknowledged. If it's successful, it tries again, and then it gives up and says, okay, failed, To mitigate that, we'll talk about several solutions. You can add power to the programming track. This is typically what gets done. You can limit the current that the keep alive device can draw, and we'll talk about how we do that. But that's a common problem related to adding keep alive devices. Other than that, we have a little bit more severe arcing and spikes if you have a short on the track, because the keep alive adds its own energy to the party. And basically what happens is all of a sudden you have this large current flowing through the track. Hopefully, none of your wheels get welded, but other than that, it's a problem that you have to anticipate. It's not a common problem, but it does happen. We talked about runaway locomotives. So typically what happens there is that your decoders come out of the factory set as dual mode, which means they'll run on DCC, but if there is no DCC, they don't detect DCC for a certain period, a certain timeout, they'll switch to DC mode, which means they'll run on whatever DC voltage they get from the track, just like a DC locomotive, right? Now, what happens when you add a keep alive device? All of a sudden, the decoder sees voltage coming from the keep alive. The track is dead, let's say, but it sees voltage coming from the keep alive, so it'll keep running. And that's when you get this runaway locomotive, right? It'll keep seeing voltage, it'll keep running. And so one of the solutions to this problem is to prevent that locomotive from switching to DC mode. And that can be done by programming CVs, and I'll show you how to do it later in the presentation. Other problems which I personally encountered and had to solve is an inrush current problem. And that typically happens when you turn on the power to your layout. You have all these keep alive devices now, 30, 40, locomotives with keep alive devices. You turn on the power and all of a sudden there's this huge current, being drawn into the keep alives, trying to load them, charge them. And the booster says up, I reached my current limit and trips, right? So that's a very common problem. And I have a solution for that, which I've used with my layout, and I'll show you later what you need. You need to add a certain circuit that limits the current for a certain period, okay? It's got a timer. It limits the current, for a certain period during which, your layout's not gonna work. We're talking about 10, 15 seconds. But your keep alive devices are going to get charged. And when they're pre-charged, to sufficiently to a certain level, you can turn on full power and there won't be any problem. Right, so I'll show you that device later. I actually have a schematic which I'll share. Okay. Now we start talking about different families of keep alive devices. So the first family we're going to talk about is what's called stay alive. Those are not full keep alive devices. What they do, if you think about it, you can compare it to a laptop, which has two types of batteries, right? It has a main battery, which operates the laptop. And it also has what's called a CMOS battery. That battery does not operate your laptop, but what it does is it preserves the laptop setting configuration, right? It preserves the CMOS, and that way, when you turn off your computer and turn it on, at some later point, the settings stay the same. And this is what a stay alive device does. Every decoder has a little computer in it, a little microcontroller in it, which stores information. I mean, which functions were on, were the lights on, what direction the locomotives were traveling, was there any momentum set, things like that. And the stay alive device keeps that information active. So your locomotive will not function while there's no power, but as soon as power is restored, it's going to go back to exactly where it was before the power went off. Okay, so this is what you need to remember. Stay alive devices preserve the state of the decoder. They don't actually operate the locomotive. But the advantage of using them is that they're typically much smaller than a full keep alive device. And they're simpler to implement. And in some cases, they're good enough. But if you have a problem of, locomotives getting stalled on dead track, it's not going to move your locomotive out of the dead track. But if that's not your problem, it's just a temporary, power interruption or something like that, stay alive might be good enough for you. Now, moving on to the keep alive devices. Those devices actually operate the decoder fully. Lights, sound, everything, right? So in the past, it was very difficult to construct keep alive devices because the kind of capacitors, the kind of storage devices that were needed to store enough energy to operate an engine were just too big, right? If you look at some of the larger capacitors that we have from those days, I'm talking about 10 years ago and before that, they were typically a few inches in size. I mean, that's too big to install in a locomotive. Technology advances actually let the industry produce what we call supercapacitors, which are very high value capacitors. We're talking about farads, complete farads. For those of you that are into electronics, a typical large capacitor would be 220 microfarad, so 1/1,000,000th of a farad. We're talking about entire farads here, which is a huge capacitor, more like a small battery, right? So those capacitors are not produced. Their sizes are typically less than 1/2 inch in length. So now we can install them in a locomotive. It's much less of a problem. So they preserve the state of the decoder and they operate the decoder, the locomotive completely. Obviously, they require more power than a stay alive device, and so they may cause this inrush problem that we talked about before. But as long as they're charged properly from the track, they'll do their function and they'll keep your engine running. You may invest a little bit. You may have to invest a little bit in a new programming booster to get more current into your programming track, so that you overcome this problem of the current that's being drawn by the keep alive. And some of them work better with decoder support. They're more efficient, and some of them actually require decoder support. And now we're going to get into the two different families of keep alive devices. I'm going to move to the next slide. Okay, so this is a very basic scheme or schematic of a keep alive device. This is what's called an unregulated keep alive device. And why is it unregulated? Because you pump in voltage from the track directly. You store that voltage as is, and you pump it back to the decoder when the track is dead. That's compared to regulated keep alive devices. Those devices reduce the voltage or convert the voltage to a much lower voltage, which fits better certain types of those supercapacitors. And as a result, you're loading the capacitor with no more than 2.7 or 3 volts. You have to convert it back to 13 volts and drive it into the decoder. So it's more complex. There's more electronics required. It's more expensive, and it has to work in tandem with a compatible decoder. And typically, the only manufacturer I know that used that method of regulated keep alive devices is Lens. They actually existed before most of the current keep alives, which are unregulated. The reason that they had to reduce the voltage to 2.7 volts is, again, those capacitors only supported 2.7 volts, and they still do. So in order to implement an unregulated keep alive device, there was a trick needed, and I'll show you that in the next slide. Okay, before we move on, just wanted to mention one more thing. What you see here in this schematic is a capacitor, which is where the energy is stored. But in addition, you have a diode and a resistor. And the reason for that is that when we discharge the keep alive, when we wanted to drive the motor, we want full power. So in this case, the voltage flows through the diode. There's a small drop of voltage on the diode, but other than that, everything goes to the decoder and goes to the motor, full power. But when we charge the keep alive, when track is connected, we don't want to draw this kind of power back into the capacitor. It's going to disrupt the operation of the engine. It's too much. So what we do is we limit the charge current. And the way we do that is we put a resistor here, which will slow down the charge and reduce the current. And this is why you have these two devices here connected in parallel. Okay. So what do we do about the voltage problem, right? The track has 13 volts. Typical capacitor like this is 1 farad, which is great. It's a big capacitor, but can only drop 2.7 volts on it, or 3 volts. And some capacitors support 3 volts. So what do we do? What TCS came up with, and basically everybody else followed, is they connected those capacitors in series. Now, what happens when you connect capacitors in series is the opposite of what happens when you connect resistors in series. When you connect resistors in series, you add up the resistance. So if you have 500 ohms, resistors connected in series, you get 500 ohms. With capacitors, it's the opposite. If it's a 1 farad capacitor, you connect 5 of them, you get 0.2 farad of total capacitance. So your capacitance goes down, which means you're going to be able to store less energy, but you can support the sum of all the voltages. Now, 2.7 volts times 5 gives you 13.5 volts. That's good enough for DCC operation, and that's what they did with the 2.7. 3 volts, obviously, you can, if you're okay with 12 volts, total, you can go with 4 capacitors. I'm still using the 2.7 volts capacitors personally, and that's because they're smaller and gives me more flexibility in fitting them into locomotives. But, it's a choice. Obviously, because we don't have to regulate the voltage, we don't have to convert it to a low voltage and convert it back. This type of keep alive device is simpler, it's cheaper, it's more versatile. So that's the more commonly type of device that you're going to find in the market. Some examples of keep alives and installing them in a decoder. So as you can see, this one has 6 capacitors, which allows it to support even higher voltages. We typically protect the capacitors, and I'll show you how, so that they don't get, there's no over voltage on them. But going to 6 capacitors ensures that you're in a safer range. This actually shows you two different ways that you're going to need to connect the keep alive device to your decoder. So typically there's 2 wires that are going to come out of it. One is blue and one is black. The blue wire, or sometimes it's white or red, will connect to your blue function wire coming out of your decoder that you typically connect to the different functions, the lights and so on. That would provide the decoder with plus, right, with the plus line. The negative line is where it gets more interesting, because typically there's no line outside that goes outside of the decoder that would have that negative. So you need to connect it in the proper way, in the proper place in the decoder, and that's typically behind your what we call a rectifier bridge. So you have a diode bridge that rectifies the DCC voltage. Remember, DCC is like AC. You rectifier into DC voltage, and right behind that rectifier bridge is where you would have a negative wire, and that's where you would connect your keep alive. There's a good website, which I actually mentioned here, that gives you a lot of examples of existing decoders and how they need to be connected. One thing I want to remind everyone, and I'll stress that over and over during this presentation, never connect a keep alive device directly to DCC. You're going to get, it's going to stop functioning for sure. You might get some smoke and other things, other bad things. So never do that. You have to find the right instructions for the specific decoder that you're dealing with and connect it there. Okay, next slide. So for those of you that are thinking about implementing a Keep Alive device yourself or building a Keep Alive device yourself, it's actually quite simple. The schematic is on the right, you can see, and I've actually given 2 examples of circuit boards that I developed for those things. Typically I don't even produce them myself anymore. I used to, but now I just, load it up on the web and a certain company will send me a ready-made PCB within a week or so for very, very low cost. We're talking about 50 cents a piece. Basically what you see here is the 5 resistors that are capacitors that are connected in series. You see the diode that we talked about before that is used to basically pump the current back into the decoder in case of the Keep Alive is being used. And the little circuit here is replaces the resistor that you saw earlier that we used to charge the capacitors. And this circuit actually does something different than a typical resistor. It limits the current, but it also limits it to a fixed amount. So your current, it's called a current mirror or a current limiter. And basically what it does is no matter what the voltage on the capacitor is, what voltage flows or drops on it, it will keep the current permanent or fixed. And so, this allows you to charge the device in a much more controllable way and prevent current spike, spike of current, which might trigger your booster to say, okay, over current, I'm shutting down, right? So this stops this problem at the Keep Alive device. And it's actually not very complicated. As you can see, it's only 2 MOSFET transistors and 2 resistors to implement. So it's pretty simple. The 2 transistors are actually one device. And surface mount, in my case, I used surface mount to save space. You can get it mostly in surface mount form. Otherwise, you can just get the through-hole device and use it. You might have a little bit more of a problem with space, but other than that, it's very simple. And the long PCB that we have here is the one I use most often. As you can see, it's only 9.4 millimeters wide, and it fits well into long hoods, diesel locomotives, sometimes in steam locomotive boilers, tenders if they're long enough, and so on. This example is the exact same circuit, but I integrated it with the main board of, this is a Bachmann locomotive that you'll see later. It's a Bachmann 460, a pretty small locomotive that I just, replaced the main board that came with it, which was in the tender. And this is the new main board. It's 100%, drop in into your tender. And what I added here is a 22 plug spin connector for a decoder. So basically the capacitors are laid around here. As you can see, there's connections to the engine, to the, some diagnostics connections here. And this connector here is for a decoder. So you get everything in one pack, and I'll show you how neatly this is laid out. Size is basically dictated by the tender. You can do this again, similar circuits for other engines as required. Okay, so some of the decoders we mentioned that already come with a Keep Alive device connection point, either a connector, a wire with a connector, or just 2 solder pads. And that, makes it easy to basically connect a Keep Alive device. You don't have to worry about finding the negative line and those kind of things. Typically, these are newer decoders. Older decoders may not have that kind of connection, then you have to do the work. Some of them, as I mentioned, very few may not even work with keep alive devices, and in that case, you're going to have to replace them. One other thing to note, non-back EMF decoders, that means they don't have cruise control or speed control, loop control. Those decoders may experience a drop in speed when the keep alive kicks in. The reason is that the keep alive stores a certain voltage on the capacitors, right? 12 volts, 13 volts, it's limited to a certain voltage. If track voltage is higher than that, when the keep alive kicks in, it's still going to supply the voltage that's stored in it, minus the little drop on the diode. So you're going to have typically lower voltage than what you get from the track. And, you'll note a drop in speed. It's not a disaster. Usually your main concern here is if, you hit a dead spot, is to get out of the dead spot. And that's going to still happen. But just, you can anticipate that. That's pretty typical. That's not something that's abnormal. Here we come to disabling the remember the conversion to DC mode. Keep your engines from running away, right? How do you do that? So CV29, most decoders, and this is standardized by the DCC, by the NMRA DCC protocol. So CV29, which is the configuration CV, the main configuration CV, typically comes with a value of 6 as a factory default. You want to change that to 2, and what that does is it turns off the bit that actually is responsible for conversion to DC mode. Now, if your engine is not going to convert to DC mode, it's not going to run away, right? The worst thing that can happen, it'll run a little bit forward and then stop. Very short, distance, and that allows it to basically overcome most of the cases where you have dirty track or dead spot, but will still prevent it from running away. Okay, so this is what I typically do. I change CV29 to the value of 2. In some cases, especially if you're talking about sound decoders, you may need to get a programming booster, and there are several products available in the market. This is especially if you're worried about reading CV values. That heavily depends on the acknowledgement mechanism, the current that we talked about. And we need to be able to supply enough current to overcome that problem. So get a DCC booster if your programming stops working. Okay. Again, you have to make the choice whether you want to go commercial or you're going to try and build a keep alive device yourself. I think the first one is going to be the hardest. Once you build 1 or 2 of them, you get used to it, and it can save a lot of money. So I built almost all the keep alive devices I use. In some cases, I had to modify the design. In some cases, I didn't even use a circuit board. I basically wired them directly so that I can place the capacitors in available, spots inside the engine, wherever there's some available space. I used it for capacitors. And that's especially important if you have small switchers and, limited space. Again, I'm going to repeat the warning, never connect a keep alive device directly to DCC. I guess you all know by now. Okay. I think we skipped. Yeah. Okay. Overcoming inrush current. So we mentioned this problem that when we turn on, power to the layout, we all of a sudden get this huge current flowing into the keep alive devices, charging them. And as a result, your booster is going to shut down, thinking, you have a short somewhere. So what can we do? I actually devised this little circuit here that, so the first part of this circuit is actually just a power supply. It gives me 12 volts DC out of the track voltage. regulated 12 volts. It's the device used here is an LM7812, which is a standard, you know, almost the most commonly used, you know, regulator, 12-volt regulator. Then we have another very familiar device, the 555 timer. Anybody who ever dealt with electronics, you know, knows this device. It's got tons of circuits around it. And the one that I've used is just a basic timer. I used a variable resistor here to be able to control the time, which is a few seconds, right? And what that device does, this is just a protection diode, but what that device does is it operates a relay, all right? And that relay, when it's not on, current can only flow through this choke here, and we'll talk about this choke in a minute. When the relay gets activated, which is after the timeout, it will bypass this choke, and the current will flow directly from the booster to the track. All right? Now, what does the choke do? This is the trick here. A choke, unlike a resistor, you know, will not resist too much DC current, but it will have high, you know, reactance, and it will basically block the energy coming in AC in you know, in any kind of higher frequencies. And DCC tends to be 10 kilohertz, you know, similar to 10 kilohertz AC. It's a square wave. It's not exactly AC, but that's what it's similar, you know, to. And so what the choke does is limits the energy that gets passed through it when you introduce DCC to the track without actually consuming energy. So it'll just block it. It will not heat up or anything like that. Some energy still goes through, and that's enough to charge your keep alive devices. And during the timeout period, those keep alive devices get charged. And, you know, when the timeout occurs, basically the choke gets bypassed, and then the layout can fully operate. By that time, most of the keep alive devices are already pre-charged. So you won't have a problem of too much current flowing through. To be honest, I only needed one of these devices for my entire layout. And I have an 8-amp booster, a good, decent booster. I had no problems with this. And I didn't even bother, you know, producing a circuit board for it. I built it on a pref board. I'll show you a picture of this device later in the presentation. Just so that we can have everything covered, this is the part list for the keep alive device that you saw the schematic in the PCBs earlier in the presentation. So we have the capacitors here. We have a diode, a Zener, which protects the capacitor, limits the voltage across the capacitors. And this FET and these couple of resistors here construct the fixed current, you know, current mirror device, current limiter device that allows us to control the charging of the capacitors and prevent overcurrent. And then there's just a connector to you know, connect it to the decoder. And this part list is for the timer device that you just saw. And again, I don't think there's anything special here. There's a very common components that you can get anywhere, Mauser or DigiKey, or in most of them in Micro Center even, they're available. Okay, a few examples. Here's two versions of the same locomotive. This is this Bachmann Spectrum 460, and we're looking at the tender. So the older locomotive was an analog DC locomotive. There was no circuit board in it. It was just, you know, an engine. The motor was in the engine. There was not much in the tender. So in order to install everything here, and I have a sound decoder here. So you can see the decoder lying underneath here. It's a 9-pin connector that goes to it, and the speakers on top. And then this is the keep alive device. And I've used the long long version of the Keep Alive device here with the 5 capacitors. It fits into the tender. It's a little bit, tight, but it works. And just for comparison, this is what I did with the DCC version of that locomotive, the same locomotive. So it had a main board here, which had an 8-pin, socket in it that you can install a decoder and a few diodes to protect the current and so on. I replaced the main board with the circuit that you saw earlier. Those are the Keep Alive capacitors. The decoder is a new decoder. It's a sound decoder that has 22-pin connector here. And by the way, the 22 and the 21-pin connectors, there are 2 different connectors types. They both have the ground negative line that you need for Keep Alive. So if you use that connector, you can use the line that comes out of it, which is the ground, to connect to the Keep Alive. So this decoder is my own development. It's a sound decoder, and the capacitor is, you can't see it from here, but it lies underneath the main board here. I had to drill a few holes in the bottom of the frame to allow the speaker to work correctly. But this is a lot neater and nicer than what I had to do with the analog locomotive. Another example, this is a Marklin engine, and it's actually quite small. It's a switcher. And in order to install a Keep Alive device here, the decoder, by the way, is a TCS decoder, TCS M1, I believe. Not a sound decoder. There's no space for a sound decoder here. But for the Keep Alive, I actually used the packed version with the smallest circuit I could think of, and I taped it to the roof of the cab, under the roof of the cab. Used the double Scotch tape, double-sided Scotch tape, taped it to the top, and that's where it is. So you can get creative. And you can actually separate those capacitors and wire them separately and locate them anywhere you have space in the locomotive. And this is my little delay device, current limiting device. This is the relay. Here's the 555 timer. This is the choke I've been using. It's a ferrite core, by the way, ferrite core choke. You can get it in many places, or just take it out of an old radio or some other device. And that's all it is. There's 2 lines from the booster, 2 lines going out to the track, and it takes care of the problem. Here's the little trimmer that allows me to control the period, the delay period. I didn't even bother, I used the perf board to build it. Didn't even bother to produce a circuit board. Okay, a few references where there's good descriptions of, Keep Alive devices, what's available in the market, building your own and so on. I think one of the best sites is the first one. Has a lot of information and, a lot of examples of decoders and how to install them. But these are also quite helpful, and you can also follow some discussion groups, and get more information as you need. I wish everybody a lot of success in building your own Keep Alive devices, enjoying them. Mine actually helped resolve a lot of the problems during operations. And with that, any questions if you have? I think if you can unmute people, unmute everybody. Yes, thanks. Any questions?
Hey, Gil, it's Bob Sprague. Thanks for the great presentation. I was wondering, is it overkill to use a Keep Alive, say, to keep the lights in a caboose or a passenger car from flickering? You wouldn't need a decoder, but you'd obviously need a rectifier to...
Yeah, I think it's still an overkill because typically, and especially if you use LEDs for lighting, the current that, or even grain, bulbs, the current that they need is much smaller than a typical motor. So I wouldn't install a complete keep alive. I would install something like a capacitor, maybe a 2200 microfarad capacitor if you have space for that. Hook it up with a diode, with a rectifier, and that should be enough. I have used the keep alive, and even that was, marginally sufficient with a camera installed in a car. You'd be surprised, but those Wi-Fi cameras tend to consume a lot of current. So, but yeah, just for lighting, I would say a capacitor should do it. Something like a stay alive device that we talked about during the presentation. Does that
Well, thank you.
answer? Sure. I did want to mention one thing which I briefly touched about, in the presentation. I get this question quite often about N-scale, and can we use keep alive devices with N-scale? So TCS came out with 2 devices, the new versions of the K1 and K2 that they market for N-scale. My opinion is, while they're small, they're not that much smaller. They may fit, well into large N-scale locomotives. Small N-scale locomotives, they're still too big. And there are other solutions. There are what's called surface mount components, smaller capacitors, smaller values as well, that can be used for that. N-scale does require less energy, but not much less energy. So you could try something like that. It will not run as well as HO scale, in my opinion. Would definitely not give you the time spans that you get with the operation times that you get with the HO scale keep alives, but it's still useful, somewhat useful to install, to try and do something with those devices. The surface mount capacitors, last I checked, were in short supply now. They're hard to get, and well, a lot of things are hard to get nowadays. But there were somewhat limited supply, and they're more expensive. They're a lot more expensive than the super capacitors that I showed here. But it's just sort of an option. Any other questions? Well,
Hi, this is Jerry. I have a quick question for you. We recently conducted a clinic here at the Hobby Barn on engine repairs. One of the things that I discovered during that clinic is that by overdrawing power from the engine, that we can actually burn the motor up. Is there any possibility of that with these keep alive devices and stuff?
It's no worse than connecting to the track. You're not getting anything different than the track. It's basically just supplying the decoder with the same voltage, or actually lower voltage than what you would get from the track. Mm-hmm. So I don't see that, because the keep alive is not connected directly to the motor. Mm-hmm. It's supplying energy to the decoder. So as long as your decoder and motor are matched, and you operate the engine with the decoder, it's the same as putting it on the track. It's no different.
Okay.
So I don't think that's a problem. Does that answer your question?
Yeah, yes, it did.
All right, thanks. Any other questions?
Thank you, Gil. Does the capacitor bank generate any heat?
Say that again. I'm sorry.
Does the capacitor bank generate any heat?
No. I've had no problems with heating up, not at all. Yeah, it is a high value capacitor, 1 farad, but we don't draw it, we don't charge it above its limits, and drawing even 1 amp from this keep alive is not a problem. I haven't had any heating problems with it.